This is the third experiment of Make Electronics, second edition by Charles Platt. We've been understanding a little bit better how to think about electrical circuits using the water flow model of electricity. We explored the idea of current as being the rate of flow of electricity in a circuit, and the idea of a voltage, which has to do with the pressure that comes out of, say, a battery or other source, propelling water or current in this case through a circuit. And we've built a very, very simple circuit, which is just a short circuit, extremely low resistance. In this case, we did it by just connecting two wires of the end of a battery strap together. And by making such a low resistance circuit is equivalent to putting a huge hole in our charge reservoir in the battery that quickly drained our battery of charge, leaving us with no voltage. Now, of course, these short circuits aren't very useful. We want to make real circuits. And so the first thing we have to do is add some resistance or constrict the flow of electricity by adding devices called resistors. Well, we've noticed that human skin and our tongues have resistance, but it's much more convenient to use discrete components called resistors, and they're shown here, the 2.2 kilo ohm resistor and the 1.0 kilo ohm resistor below it, and I've used the resistor code to write out what these resistances are. When you pick up a resistor, you'll see a series of stripes of different colors. Usually 3 will be grouped to one side, and they'll be one of the colors that are shown, running black through white, and there'll be a gap between bands, and then there'll be a tolerance resistor, either usually a silver or a gold resistor. We're going to talk today just about those first 3 stripes, which is how you can tell the value of the resistor. Again, the unit of resistance is ohms, written as the capital Greek letter, omega. The first 2 digits are given by the first 2 colors. So, for example, if you saw 2 red stripes, it would be 2,2. Resistances, however, cover a broad range. As we've already seen, our human skin had ranges in the mega ohms, and many of the components we're going to use actually have resistances down to only a few ohms, or 1/1,000,000th the size. So it's important not just to say what the first 2 digits are, such as a red is a 22, but how many zeros follow. So if I actually had 3 red stripes in a row, red, meaning 222, that would be 22 and then 00, 2,200, or 2.2 kilo ohms. And then again, there's the gap, and then the stripe in a metallic color, usually silver or gold. We will get lots of experience reading resistor codes, but it's also important to be able to check them using your multimeter before using them in circuits. So let's get out our ohm meters, set them to the ohm setting, and then we're going to look at the 2.2 kilo ohm resistor, which reads red, gold, 2200, 2.2 thousand or 2.2 kilo ohms, and by putting our meters on the 20 kilo ohm scale, we read about 2.18 kilo ohms. If we go to the lower scale, the 2 kilo ohm scale, 2.2K is bigger than 2.0K, so we read an overload on our manual ranging meter. And if we move to the higher range, which is 200K, we find that, yes, our resistor is about 2.2K, but we got less significant figures. So the proper setting to measure the 2.2 thousand ohm resistor is the 20 kilo ohm setting. Now let's look at the 1 kilo ohm resistor, 1000, or 1000 ohms. We can start by trying to measure again the 20 kilo ohm range, and we'll find it will work. We'll read 0.99 kilo ohms, or 990 ohms. But to get an extra bit of precision, we can actually jump down because we're under 2K. We find it is 0.989 or 989 ohms, a very precise reading. If we continue to drop another range to the 200 ohm range, it should read an overload. Again, that's a 1 on this meter on the far left, because we're considerably larger than 200 ohms and we can't read on the scale. Let's jump up a couple. So now we're on the 200 kilo ohms setting. We only get 1 digit or so of precision. If we try to jump up another one to the mega ohm setting, we really just aren't able to get an accurate reading at all. So again, you have to find the right range, and that right range is going to be the lowest range on your meter that still gives a reading. Now, it's really important that you not use your fingers to measure resistances unless they're very small resistances. You want to be pushing it against a table or a non-conductive surface, piece of paper or wood. A wood table is fine. If you use your fingers, you're measuring a little bit the resistance of your own body, and like we found, that isn't always negligible. Now that we understand how to measure resistances and how to use a resistor code, let's talk about what we learned about how we might use those resistors to change the properties of circuits using the intuition we've been developing, which I've been calling the water flow model of electrical current. So this idea is illustrated in figure 131 in the textbook. And the first main concept is that the electrical flow of electricity per second is measured in amperes or amps. So that's the amount of water that sort of comes out of this bucket that has a hole in it. The pressure that's pushing the water out of that hole is called voltage and measured in volts. And the size of the hole determines the rate of flow given that voltage. And that's what we call the resistance. And we measure it in ohms, which uses that Greek capital letter symbol omega. We've been selecting resistors from different ones in our box. When we increase the resistance, that is making the hole smaller and the current goes down. And if we increase the voltage, we're better able to overcome that resistance and still obtain a high level of current flow. With a model of electrical circuits in mind, we're ready to build our first useful circuit, which is going to be lighting up a light emitting diode. Let's get out our package of small parts from the kits and select one of the red light emitting diodes. Notice it's got a short leg and a long leg. That fact will become important. Grab 3 of the leads, and to start with the 2.2 kilo ohm resistor. Now I understand that's the red gold labeled resistor. We're also going to need our 9-volt battery and have a 1 kilo ohm resistor on deck. We're going to just be clipping our leads straight to the battery for these first couple simple experiments. And by convention, I'll use the black lead on the negative side of the battery. That's one with the larger of the 2 terminals. You can see that goes to one end of the resistor. And then I'll just use a green for a neutral color. You can use, of course, any colors you want of the available alligator clip leads to connect that resistor up to the short leg of the LED. So again, get out that LED and make sure that you can tell the difference between the short and long legs. That short leg should always go on the negative side because a light emitting diode only permits a one-way flow of electricity. There's the short leg. And you can bend the leads apart slightly, but don't separate them or pull them out. But you want to bend them apart enough so that you don't short out the 2 legs of the LED by touching wires. So spend a little time. Get it so everything lays nice and flat on your surface. Again, you should be using a non-conductive surface like a wood table or on top of a piece of paper. And we're going to take one remaining wire and connected from the long leg of the LED to the smaller terminal, which is the positive terminal. And there, it lights up. We've made our first circuit. If I disconnect anywhere the circuit, it'll turn off. Now we're going to do a couple of other quick checks to understand how to troubleshoot circuits that might not be working. Easiest to learn it with a circuit that works, and my favorite method is to trace around the circuit diagram and the circuit together. So you can see my mouse is going over the original circuit schematic in the lower left corner, while my pencil is tracing the same route through the circuit, and notice that my pencil never lifts off the paper, neither does my mouse pointer. Let's do it again. Start from the positive, go through the LED, and then through the resistor, and back on the black wire to the negative terminal. Never lifting up, all one trace, and that's how it's tested. Let's take a moment and swap some components around and see what happens. First of all, let's change the 2.2 kilo ohm to a 1 kilo ohm resistor. Now we imagine this is sort of like the kid in the diagram, not standing quite as hard, right? Lower resistance. And so given the pressure of 9 volts, we expect to see a bit of a brighter light due to having more current. If we flip the resistor, we don't really expect the direction of the current to matter in the resistor, and we should get the same result. However, if we flip the battery, because the LED only allows one-way flow of electricity, we won't see the LED light up. So this could be something that is wrong with your circuit, that the LED or the battery is in the wrong direction. So that's with the battery flipped. Next, let's try the LED flipped. Again, you want to have the long leg on the positive end and the short leg on the negative part of the circuit. So we're going to flip that around and now mistakenly put the long leg towards the negative end. And so the LED won't light this time. Right. But that's something you'd want to flip around if you thought you'd have a problem. Check your LED orientation and make sure that that long leg is always pointed towards the positive end of your circuit. For the assignment, this experiment, please try to repeat the measurements as shown in the video and do read through the textbook. I'd like you to start sorting your resistors. You've got a whole bunch of resistors in your kits. Make a table of which ones you have, how many of each, and then compare the nominal value, that is according to the resistor code, and the reading that you actually get on the most accurate scale. Now next to it, please do include the precision, that is a gold or silver rating. We'll talk more about that soon. And include all the decimal points you can read. Remember, you want to use the highest resolution on your meter that's available. The next part I would like you to do for the assignment is to replace the 2.2 kilo ohm resistor in the circuit shown in figure 1.45. Try a bunch of higher resistor values, but don't try lower resistor values because you might burn out your LED. So maybe the 4.7 kilo ohm, 10 kilo ohm, and 100 kilo ohm, for instance. Describe the relationship between resistance and brightness, and try to explain what's happening in your logbook. And then finally, I have a little design challenge for you. Notice I swapped the direction of the resistor, and the circuit worked just fine. I swapped the direction of the battery and or the LED, and it didn't work. Now instead, what I'd like you to try doing is swap the position of the LED and the resistor in the circuit relative to each other. So in other words, put the resistor closer to the positive end and the LED closer to the negative end. Can you figure out an orientation to get it to work? Explain why you think it does or doesn't work and what you had to do